Module 11, Chapter 21. Now, the human body has to be able to protect itself from two things. One are pathogens. Pathogens are viruses, bacteria, fungi, and other types of microbes that can enter the body and cause disease. However, you also have to protect yourself from non-living disease agents, such as toxins and radiation. Now, there are three basic lines of defense in the human body. The first line of defense and the second line of defense are both non-specific defenses. The third line of defense is your specific immunity. Now, think of it at a first line is that these are the structures that a pathogen would encounter, and it's their responsibility to keep that pathogen from even getting into the body. So your first line of defense is going to consist of external barriers, which are impenetrable to most pathogens. So these would be things like your skin and your mucous membranes. Now, if the pathogens get through the external barrier, the second line of defense is designed to try to combat that pathogen and prevent it from getting any further. So the second line is dealing with the things that can make it through the first line. So these would be your leukocytes, so the neutrophils, the monocytes, the eosinophils, variety of macrophages, your antimicrobial proteins, your natural killer cells, even inflammation and fever serve as second line of defense. However, if the second line of defense is not enough, that's when you can pull in the third line of defense, where you bring in lymphocytes. And you use their ability to specifically attack the pathogen at hand to defeat the pathogen and leave behind a memory of it for a faster response the next time the pathogen tries to make you sick. Now, nonspecific defenses lack the ability to remember a pathogen or react differently to it in the future. Because remember, nonspecific means they just are designed to block things, eat things, and they don't discriminate between what type of invader it is. Which means that they defend equally against a broad range of diseases. And these mechanisms are present from birth, and there are three major types of nonspecific defense. You've got protective proteins, you have protective cells, and then you have other protective processes. In specific immunity, which is sometimes referred to as adaptive immunity, you do have the ability to be adaptive, meaning the body can adapt to a given pathogen and ward it off more easily the next time it tries to invade. And it is specific because your body must develop immunity for each type of pathogen it encounters. So in order to have specific immunity, you have to be exposed to the pathogen first in some form, either by getting sick or getting a vaccination, but you have to be exposed to it in order to build it up. So now let's walk through our different lines of defense and look at the things that are going to contribute to them. The first I want to talk about are your external barriers, which are your first line of defense. Now, if you think about external barriers, the first one that should leap to mind is your epidermis. Remember from A&P1, the outer layers of the epidermis have been keratinized, meaning the cells developed keratin protein within them, which helps to harden the cells, so it makes them physically hard. And because all of the cells are linked by tight junctions in those many layers, it's very difficult for pathogens to get through that barrier. Also, the surface of your epidermis is way too dry and way too poor in nutrients to help support the growth of many types of microbes. Your epidermis exfoliates, meaning the outer layers of the epidermis are constantly being shed, and when those cells are shed, the pathogens on them are carried away too. You have the acid mantle covering the surface of the skin. This layer that contains lactic acid and fatty acid, and that acidic nature does help to inhibit bacterial growth. There's dermacidin, which is an antibiotic peptide, which is part of your sweat. You even have things called defensins and cathelicidins, which help to destroy bacteria, viruses, and fungi. Your mucous membranes, such as the mucous membranes lining your mouth and the rest of your GI tract, the mucous membranes lining your respiratory tract, they produce mucus on their surface, and that mucus is sticky, and it helps to ensnare microbes so that they can't travel any further into the body. The mucus also contains a chemical called lysozyme, which is an antibacterial peptide that also helps to kill bacteria. Areolar connective tissue contains hyaluronic acid, which makes it very viscous and sticky. And you learned that epithelial tissues overlie connective tissues. And in many cases, they're overlying areolar connective tissue. So even if something gets through the epidermis, it could get hung up and snared in this really viscous, sticky areolar connective tissue. The hair that you have in your nostrils serves as a really good filter for incoming pathogens. You also have cilia lining your respiratory tract, which helps to move mucus, which contains the pathogens that have been trapped, and move that mucus up out of the respiratory tract so that you can cough it out or swallow it and kill whatever's in it in your stomach acid. The lacrimal apparatus produces your tears, and your tears contain lysozyme, that antibacterial peptide, but also if you just think about it, your tears are made out of water. So you have tears constantly flushing the surface of the eye, washing debris and pathogens off the eye's surface. So it's protecting you by having this great flushing action. Your saliva in the mouth, exact same thing. Saliva contains lysozyme, and it's a great flushing action for the mouth where you can flush food debris and pathogens off your teeth, off the linings of the cheeks, and spit it out or swallow it. Your urine flow is an external barrier. If you have bacteria trying to migrate up the urethra, which is the tube that carries urine out of the body, just the act of urination flushes the urethra and washes those pathogens out. Also, urine is acidic, and many microbes are very sensitive to acid, so you might actually be able to destroy some of the bacteria trying to get in. Vaginal secretions accomplish the same goal as your urine flow. They help to flush pathogens and debris out of the vaginal canal. It's also acidic, which is going to inhibit the growth and survival of certain types of microbes within the canal. Defecation and vomiting both give you a very fast physical removal of material from the body. So you can defecate out the pathogens, vomit out the pathogen. Your sebum, which is the, you call it body oil. It comes from your sebaceous glands, covers the surface of the skin, helps to lubricate the surface of your skin. And if your epidermis is lubricated, it stays nice and moist, nice and supple, and it doesn't crack. So it stays a nice continuous barrier. If your skin gets dry because you don't have sebum on it, it starts to crack. And that means you're taking that great external barrier and you're making small crevices within it that microbes could take advantage of, get in, and make you sick. Your sweat contains dermacidin, that lovely antibiotic peptide. However, sweat is basically your body's natural shower. When you sweat, it washes the surface of your body. So it's washing off all the dirt, all the debris, and it's washing away the microbes. Your gastric juice. You swallow pathogens that came out of mucus from the respiratory tract, or you ate pathogens with your food. Your stomach gastric juice is highly acidic. It's like pH 2 acid. Most microbes are extremely sensitive to acid, and that environment is quite hostile, and it can kill a good number of different types of microbes. Your second line of defense is going to include your leukocytes and macrophages. Now, these cells are going to help you remove cellular debris, foreign compounds, and pathogens. Now, for the 4 types of leukocytes, the neutrophils, eosinophils, basophils, lymphocytes, and monocytes, you have already been directed in your blood lab to copy the summary functions from your formed element table in your lecture textbook into the white blood cell table of your blood lab. And those functions for those 5 at that level of detail, you've already had to study for lab practical number 1 and lecture exam number 1. So what I'm going to ask you to do at this time is to go back and review that information. Again, the functions you need to know for each one of these 5 is in a table already for you in the lecture text if you have not copied it over into your blood lab table. Now, we've already mentioned natural killer cells and that they provide what is called immunological surveillance, which means they travel throughout the body, basically monitoring your normal tissues, looking for things that are abnormal. And they have the ability to respond to and attack any cell with an abnormal plasma membrane, meaning they're not selective. So this is again that nice second line of defense, nice and non-specific. Now, natural killer cells are very helpful because they do have the ability to respond more rapidly than any T or B cell. So when there is something abnormal, these can actually step into the gap first, start killing those cells while you are activating your specific immunity. Now, they're very good at attacking bacteria, transplanted tissues, viral infected cells, and cancer cells. What's interesting, though, is how do they actually go about killing your abnormal cell? So what we have on the screen here is we have on the left a little natural killer cell, a little NK cell, and it has found a foreign cell. They're calling it in the figure an enemy. The first thing your NK cell will do is it's going to release something called perforin. Perforin has the ability to actually create holes in the plasma membrane of that foreign cell. Now, by popping numerous little holes in the plasma membrane, you allow for what is called cytolysis to occur. Cytolysis is a rapid inflow of water and salts into the cell that actually leads to rupturing of the cell itself. Now, the NK cells also can release things called granzymes. Granzymes are protein-degrading enzymes that also have the ability to enter the cell and destroy its proteins. So it can actually attack the pathogens on the inside of the cell. Now, in your second line of defense, you also have different types of antimicrobial proteins. So remember, proteins are non-living. Okay? These are not cells. These are just proteins that you have in your blood and your tissues. The first group of proteins I want to mention are your interferons. Interferons are small proteins released by viral infected cells. So if a cell gets infected with, let's say the flu virus, that cell knows that it's sick. And what it's going to want to do is it wants to send out a warning to all the healthy cells in the area that, hey, I have a virus. There's a virus in here. You need to protect yourself. And what these interferons will do is they will travel and spread by diffusion throughout the tissue and actually trigger the healthy cells in the area to start producing antiviral proteins. These antiviral proteins will decrease viral replication within the cell. So if the cells do encounter the virus, when the virus comes in, it's going to have a harder time replicating itself because the cell is prepared for the invasion. The interferons also can activate natural killer cells in the area and macrophages within the area. So you can turn those on as well. Now, because your interferons activate natural killer cells, and natural killer cells can attack cancer cells, the use of interferons actually starts to confer some resistance to cancer. So there are cancer treatments that use interferons to help boost your natural killer cell activity, basically your body's own ability to destroy cancer. You then have what is called complement. The complement system includes 30 or more different globulins, all mostly made by the liver. And these proteins play a role in specific immunity, and they also play a role in non-specific defense. And the complement system can begin 3 different ways. Now, in the classical pathway, it actually is initiated with some specific immunity. What's going to happen is you're going to have antibodies binding to an antigen on a microbe, right? So that's one way of initiating the complement system. In the alternative pathway, you start things by taking C3b, which is a complement protein, and you're going to have it bind directly to either a tumor cell, a virus, a bacterium, or a yeast. In the lectin pathway, lectin binds to certain sugars on microbial surfaces. So we've got 3 different ways for initiating complement. However, regardless of how you started, these pathways all lead to a common set of body responses. One is inflammation. We're going to create the inflammation by having histamine released by your basophils and your mast cells. And this inflammation is going to start to attract neutrophils and macrophages to the area. You're also going to have immune clearance. Complement is going to help you bind the antigen-antibody complexes that you form to red blood cells. These red blood cells are then going to flow out of your tissue, and macrophages in your liver and spleen actually can remove the antigen-antibody complexes from the red blood cell and destroy them. You are going to have phagocytosis. Now, this is normally carried out by the neutrophils and the macrophages. This is going to help you phagocytize bacteria and viruses and destroy them. However, it's going to be enhanced with the use of C3b, that complement protein. C3b is going to provide opsonization, meaning it's going to coat the microbe so that the phagocytes can actually bind to it more effectively, which makes them much more effective at phagocytosis. Complement can also cause cytolysis. You can actually use various complement proteins together to actually form holes in the plasma membranes of your target cells. And by forming these holes, you have that inrush of water and solutes that's going to cause the cell to swell and to rupture. Inflammation is also a second line of defense. It's a localized response to injury, and it does have some important purposes. It does help to limit the spread of your pathogen. It's going to help remove debris from your tissues, and it also helps to initiate tissue repair. So even though inflammation is not comfortable, it is important in defending your body. Now, there are 4 cardinal signs of inflammation. You have redness, pain, heat, and swelling. And believe it or not, these 4 cardinal signs are related to the events that are actually occurring during inflammation. Now, one of the first things that will happen with inflammation is vasodilation. So that means your blood vessels are going to widen, the smooth muscle in their walls are going to relax, you're going to have more blood coming into your tissue, which is called hyperemia. Hyperemia is an increase in blood flow beyond normal. Now, what you need to remember is blood carries your heat around the body. So blood temperature is about 100.4 degrees Fahrenheit. So it's a lot warmer. So if you have more blood flowing into your tissue and you have all of those red blood cells in there with all that nice red hemoglobin, hyperemia is going to create the redness. And the temperature, the heat that you feel at the site of inflammation is because you have more hot blood filling that area and you're feeling the heat from that flow. You're also going to have an increase in vessel permeability, meaning the walls of your capillaries are going to start to get very leaky. So instead of having your regular amount of filtration, you're going to have more filtration than normal. You're going to have more fluid leaving your blood and entering your tissue. Now, if your vessels are leakier and you have more fluid leaving your blood and entering tissue, wouldn't that cause edema, some swelling? So the increase in vessel permeability is going to help. It's going to create this swelling. Also, any kind of nerve damage or pressure or stimulation to your nociceptors is going to create the pain. And remember, swelling will stimulate nociceptors if your fluid volume goes up over 30%. Now, stimulating the nociceptors, it could be due to the increase in tissue volume, but at sites of inflammation, you also have other chemicals like prostaglandins, bacterial toxins, or bradykinin, which is a chemical produced by damaged tissues. These all together can also stimulate nociceptors. Fever is our last component of your second line of defense. Fever involves maintaining a body temperature greater than homeostasis. Now, to create a fever, you're going to need chemicals called pyrogens. Pyrogens have the ability to reset temporarily your hypothalamic thermostat. You learned in A&P 1 that your hypothalamus is where your body stores your, quote, normal body temperature. Whereas it knows that your average body temp is 98.2. My average temp on a regular day is 97.6. So your hypothalamus knows what your normal is. Pyrogens, however, can interact with the hypothalamus and confer to the hypothalamus slightly different information, causing the hypothalamus to temporarily assume that your average body temperature should be much higher. And your hypothalamus is going to initiate a series of reactions to raise your temperature and create that fever. Now, pyrogens come in 2 different classes. Exogenous pyrogens come from outside the body. So these are fever-producing agents, such as surface glycolipids on bacteria and viruses. So you can actually use chemicals from the surfaces of these pathogens to stimulate fever creation by the hypothalamus. Endogenous pyrogens are produced within the human body by cells that are part of the human body. For example, most of your endogenous pyrogens are secreted by neutrophils and macrophages as they are actually attacking the pathogen. So as the neutrophils and macrophages are trying to kill the pathogen, they're releasing endogenous pyrogens that will enter your blood, flow to your hypothalamus and say, hey, we're battling an infection down here. Please start spiking a fever to help us out. Now, fever, again, not comfortable. No one likes feeling those uncontrolled chills. You're miserable. However, fever has some really big benefits. One, the elevation in temperature inhibits microbial growth. These pathogens that are coming into your body love your homeostasis. They are quite comfortable at your 98.2 degrees Fahrenheit, and they will settle in comfy, cozy somewhere in the body. You raise the temperature, and all of a sudden, many of those microbes can't grow really well. Some of them might even start to die a wee bit because you're creating a hostile environment. You're creating a temperature that is not suited to their survival. Fever also increases your metabolic rate. For every 1 degree Celsius increase in body temperature, your metabolism increases by 10%. What this is going to allow you to do is have much quicker mobilization of your defenses and your repair processes. Fever also has the ability to intensify the effects of interferons and other microbial proteins in your second line of defense. So before you quickly run for the Tylenol, when you have a teeny tiny smidge of fever, you might want to consider letting the fever run its course and see if it will resolve on its own. You might find that you get better faster because you've maintained that nice hostile environment.